Alright, sorry about that there, folks. Okay, so, there was a update within the past week, so all the, everything that was, um, set on my Streamlabs has kind of been reset, so normally I was able to kind of catch it beforehand, but today it was kind of slow on handling all that. Okay, so we got ourselves a 2 p.m. PST Twitch stream. I'm your host, Strange Jim, and today we are going to be getting back into developing the game GGG using Unity. Um, if you haven't really been following at all, um, I say GGG, but it's the long version of it is called Ghouls, Ghosts, and Goblins. So um, we're going to be uh, continuing our study of um, the A stars and the pathings. So we were working on that last week. We were kind of checking that out, seeing which of the pathing algorithms was going to kind of work for us for the most part. Um, but the um, there was still quite a bit for us to kind of look at and study and see if everything was kind of um, if everything kind of worked with what I was kind of looking for. Now, some of those that was available, or some of the paths that was suggested out of the Wikipedia page. They were based off of weighted edges and weighted vertices, but I don't have that in this particular game. I'm using a flat 2D surface. There's not going to be any kind of like hills that might increase the distance or travel time or anything along those lines. So um, we don't have to worry about that per se. But we still need to figure out, what still works out of the list that we have left. There's a couple of the um, let's see. I'm looking at it now and I see about 5 different um, pathing algorithms that we're going to need to research a little bit and see which of those 5 would work well in my particular game. Now this may change, for like a like if I do like another version, like a version 2 or something along those lines. But um, we'll get to that when we get there. Okay, that's further down the line. We don't need to worry about that. Okay. What we do need to worry about is which algorithm works best um, for this particular game. So everything looks to be relatively in order. Let me make sure that everything, I don't have like, any like extra programs that might kind of get in the way or anything along those lines. So, um, slow down the stream or whatnot. So, okay, everything looks good. Let's go ahead and switch on over to live. Okay. Okay. So, for those of you that can see it here, these are the five that I'm talking about here. Now, bidirectional um, is potentially helpful in either case. Um, so we'll see whether or not that we could use it, or if we just need to kind of put it to the wayside or whatnot. So we're going to need to do a more in-depth view of A star, of D star, jump point, fringe search, and LPA. So those are the algorithms that we're going to be really going in depth today on. Now, if you have any kind of experience on these particular algorithms, then feel free to chat with me in the chat. Um, I'm more than happy to kind of talk about these. Now, I know A star. Okay, I've used A star before and on other projects. Um, but I have not used any of these other four. Okay, so if they're saying that it's more efficient or that there's a 10 to 40% performance boost, that gives me some amount of, um, I need to look in on that because if I'm going to be having all of these AI units going around the map, okay, I'm going to want to, um, I'm going to want to be able to manage their pathing relatively well. I mean, we're talking about units that could get, into the 20s, 30s, 40s. I don't know. I don't know where the balance is right at this moment in time. Okay, I might have to limit the amount of units that are out there to keep the performance to work pretty well. I don't really know. Um, yeah, obviously, I'm going to need to, um, once I get this to a point where I can demo it, then not only will I be able to kind of send it out to the general public to see what they think, but I'm going to need to kind of play the demo offline because obviously streaming and testing isn't going to be ideal. I'm not going to get the best kind of performance. Um, I'm not going to be able to kind of test out how good the game or what its cap is at based off of, um, based off of, what I have and streaming at the same time. So, um, but by that point, hopefully I've kind of smoothed things out a little bit so that we don't have to worry about it too much. We'll see. We'll see. Um, so we're gonna need to kind of let's look into the D star algorithm first off and see how good is the D star. We may take like an hour per um, seeing that I stream on these Sundays for 4 hours. I may try to tackle each one of these for an hour. I don't know. We'll see. Um, but at the very least, we're gonna need to kind of study these in depth and see why are they better than A star. If they're saying that they have they're more efficient, and I need to find out why. Again, if anyone has any insights on this, then I'm more than happy to hear hear those insights, or if you have any particular comments or suggestions or anything along those lines, then I'm more than happy to hear them. So, all right. So, let's get into this, shall we? So we have the D-star algorithm. All right. Well, we've already kind of looked at the Wikipedia, and unfortunately, it doesn't really give. Um, yeah, I mean, it gives some information, but it doesn't really give too much. So we're gonna need to kind of look into this a little bit more. So, okay. Um, we got some PDFs. Um, we got some Stack Overflows. Let's see. Hmm. Path algorithm, which is carry out dynamic search, suitable for situations where the surrounding environment is unknown. Which, I mean, that's the case of our map right at the moment. So, okay. Um, yeah, let's go ahead and open up some of these PDFs here, and we'll start kind of looking in on this a bit. We don't need to worry about the Stack Overflow. That's not really going to give us a ton of information. So, or at least not enough to make it be worthwhile in our particular case. So, we're going to go ahead and kind of skip that. You know, sometimes they do, and sometimes you can find, you know, good information um, on this, but for the most part, um, it's good for like troubleshooting or something like that. But I mean, we're going to be trying to go in depth on this. So, okay. Let's see. Any other ones that I want to bring out here? Mm, I mean, we can always look in on some of um, these other YouTubes concerning these and the D-star algorithm. I mean, that's always an option. Um, Probably won't have. We'll see whether or not I can actually add the audio into it or not. Um, but obviously, sometimes um, these particular YouTube videos might be worthwhile for you if you don't have time to kind of read through the like. So, let's see. Um, hmm. Request full text PDF. So would have to contact Anthony Steins concerning this particular research paper. No full text available. various notifications and the like. Okay. Lots of citations. Um, but I don't know whether or not this would be instantaneous, and it might tell me, hey, you need to. Well, I mean, it's saying join for free, but um, I don't know whether or not I'm going to be able to kind of get back the information right away on this. So, um, oh, one of those websites. No, thank you. I don't like when you pop up like that. Wait, what? Hmm. Okay. Interesting. I don't know why we're able to see the PDF here, but it's, someone posted it online, I guess. Okay. Okay. Find the lowest path through graph of states and central many problems. Include report lining for mobile robot. If our costs change during traverse, then the remainder of the path may need to be replanned, such as the case for a sensor-equipped mobile robot with incomplete or inaccurate information about its environment, which is something that is may happen to each one of the AI agents that are available, or that I'm going to be um, putting these paths or to allow them to travel these particular paths. So um, they may need to kind of readjust their path based off of if there's like an enemy about, or if there's um, a barrier that gets put up, or whatever. So uh, as the robot acquires additional information via its sensors, it has the opportunity to revise its plan to reduce the total cost of its traverse. The prior information is grossly incomplete or inaccurate. The robot may discover useful information in nearly every piece of sensor data. During the replanning process, the robot must either stop or wait for the new path to be computed or continue to move in a wrong direction. Therefore, rapid replanning is essential. This paper describes a new algorithm, D-Star, capable of planning optimal traverses in real time through focused state expansion. D-Star repairs plans quickly by taking advantage of the fact that most arc cost corrections occur in the vicinity of the robot and the path needs only to be replanned out of the robot's current state. D-Star can be used not only for route planning, but for any graph-based optimization problem for which our costs change during the traverse of the solution path. Now, the the pathing costs are not going to change. So the the edge cost, the node cost, those aren't going to change by weight. So goal state, minimum cost of graph. Hmm. I'm gonna kind of skim through this for the most part. I mean, this is a lot of text here, folks. um, and I'm probably not going to be reading all of it, you know. It's 34 pages of pretty condensed information, so um, I want to kind of get to the, I guess you might say, the meat and potatoes of what's going on here. So the algorithm is named D star because it resembles A star, except that it is dynamic in the sense that our costs can change during the verse of the solution path, provided that the traverse is properly coupled to the replanning process. It's guaranteed to be optimal. This section begins with the intuition behind the algorithm, defines the notion used, and presents D star as described. Signs 13. Let's see. How a start involves filling path or path planning problem. Figure 1 shows a connected graph representing a Cartesian space of robot locations. States in the graph depicted by arrows are robot locations. I'm not really seeing any kind of arrows on here whatsoever, so unfortunately not exactly ideal. Um, let's see, states of the graph. Mexico, the cost of moving between states, white regions are locations known to be in free space. Our cost for moving between free states is small value denoted by empty. Gray regions are known obstacle locations, and arcs connected to these states are signed as prohibitively high value of obstacle. Small black squares is a closed gate believed to be open. Robot is point size and occupies only one location at a time. It should be noted that planning with non-zero size and shape can be reduced to a point planning problem. Focus A star can be used to compute optimal path costs from the goal. From the goal G, which is right there, reduced to a point planning problem on focus A star can be used to compute optimal path costs from the goal G to all states in the space given the initial set of our costs as shown in the figure. The robot starts in some initial location, begins following the optimal path to the goal. At location R, robot sensor discovers the gate between the two large obstacles is closed. This corresponds to the correct arc value, and then moving through it. All paths through this arc are possibly no longer optimal, as indicated by the labeled region. Generally better than recomputing the cost map, but we're only interested in pairing the optimal paths out of the robot's current location and then continuing to move the robot. The rest of invalidated states need only be processed if the robot is forced to venture into that area. Therefore, the repair should be incremental reentrant. D-Star provides both features like A-Star maintains an open list of states for expansion. However, these states consist of two types, raise and lower. Raise states transmit path costs increases due to increased arc value, and lower states reduced costs and redirect arrows to compute new optimal paths. The raise states propagate the arc costs, add the value of gate all paths passing through it, Raise states activate lower states which sweep in behind to reduce costs and redirect pointers. Lower states compute new optimal paths to states that were previously raised. Okay, so based off of where the robot is located at, it's basically considering everything that is further away from G to be as a raised state. So um, you don't necessarily want to go towards it right away, but it is finding some directions that may be um, that might be lower than where um, than the obstacles and the race states. So um, it has the option of going to either one of these two lower states. So okay. Um, Lower states are placed in the open list by current path cost value, cost from the state to the goal. The raised states are placed on a list of previous unraised path cost values. States on the list are processed in the order of increasing value. Um, pound on the path costs of lower states they can discover. Thus, if the path costs of the lower states currently on the open list exceed the previous path costs of the raised states, then it's worthwhile to process raised states to discover possibly a better lower state. And figure that the arrow from the goal to the raised state wave front is equal to the length of the arrow. The raised state front. Okay. Oof. Hmm. Okay. This first in process, just previously invalid region. Algorithm propagates all cost updates logged to that point to this region to compute a new optimum path to its goal. As this duration, we introduce the following notations and definitions. Hmm. 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 Okay. 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 Minimum state x, if x is null, returns no value. If they are equal, then delete x, which I would imagine is just removing it from the min state. Okay. Let's see. For each state in x in the graph, you set a value equal to null. Well, t of s is not equal to closed and val is not equal to no val. Val is equal to process state, which, goes up here and checks all that out. TSS is new, then return no path. S, well, R is not equal to G, X and Y, such that S, X and Y is not equal to C, X and Y. Val is equal to modified cost, X, Y, S, X and Y, while less. Val cost R and val is not equal to no val. Val is equal to process state. Is equal to BR. Turn goal reached. Graph is disconnected, is not detected. Path is equal or obstructed by obstacles. In order to provide for this capability, obstruction arcs can be assigned a large positive value of obstacle, and unobstructed arcs can be assigned a small positive value of empty. Obstacles should be chosen such that it exceeds the longest possible sequence of empty arcs in the graph. No unrestricted path exists. In goal from S, if h of s is greater than or equal to obstacle after exiting the loop at line L5. Otherwise, no unrestricted path exists to a goal from the state R during traverse. H of R is greater than or equal to obstacle after exiting the loop at line L12. Hmm. path. Hmm. 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 Okay. Okay. Hmm. Okay. Let's see. To do this, mobile list with lowest value status. When the lowest list when Hmm. Let's see. Hmm. Shows a cluster of one harmed by one Earth state environment. Starts at state S and moves to state G. All the obstacles shown in black are unknown before the robot starts its traverse, and the map contains only empty arcs. The robot has point size and is equipped with 10 state radio field of view sensors. Okay, so shows the robot's traverse from S to G using the basic D algorithm. First is shown as a black curve with white arrows. So basically like so. Let's see. Show final cost field for all states determined during the traverse that most of the states are examined by at least once by the algorithm. Okay. Figure 10 shows the robots traverse using the focus D algorithm. Number of new states examined is fewer than basic D since focus D algorithm focuses on the initial path calculation. Subsequent cost updates on the robot's location. Note that even for those states examined by the algorithm, fewer of them end up with optimal paths to their goal. Finally, none of the two trajectories are not fully equivalent. This occurs because the value cost reverse is not unique and two of the algorithms break ties in the path cost arbitrarily. Okay. Back pointers are omitted for clarity. Black curve shows the optimal traverse to the goal. In the case where the robot knows about the obstacles before it begins its traverse, this traverse is known as optimal since it is equivalent to the optimal path to the goal. When completing accurate arc and cost information, Figure 12 shows planning in the same environment where none of the obstacles are stored in the map. Three portions of obstacles detected by the robot's 15 states. Radio sensor is shown. Optimistic optimal. Mm-hmm. Let's see. I kind of wanted to zoom in on this a little bit. Um, there we go. Okay, so you can kind of see the pathing of this a little bit. Um, it's unfortunately seeing that it's black and white, it's a little bit hard to see. I'll grant you that. Um, but so you have, your starting point here. It goes on down. It, sees the wall that's in front of it, so it starts turning. Uh, there isn't any other like additional places for it to go, so it moves down this way, continues on down, finds that there's still like walls here, so it kind of starts like backtracking over to this way. Now, if it had just gone a little bit more, it could have seen this gap here and probably could have gone, um, it could have kind of gone around this corner and started like going back this way. But at the same time, um, how is it supposed to know that, this right here is the optimal path? And if it's only seen a certain distance kind of thing, then it might be like, well, I can't see anything beyond it, so I'm going to have to turn around. It's going to be quite, it could potentially happen. Even with my AI agents, okay, it might see that trying to go through this path here might be more, you know, uh, or there might not be even be a path there. It might be completely like blocked off here. You're not really seeing it because um, the um, you know uh, the sensors and whatnot can only see so much. So it sees this gap, which is closer to G than over here. So it goes back, finds a way to kind of continue moving on towards G, starts moving in that general direction, moves again, finds out that this entire area is blocked off, so it turns right back around, looks at this particular gap. Now, you might be wondering, well, why didn't it just go here in the first place? Well, between this gap here and that gap there, this gap is slightly, not by much, but slightly closer to G. Now, its sensors on the robot were larger, meaning that it can kind of go, of a larger radius, then it might have already seen the fact that, this area was kind of blocked off. Probably not. It would have probably had to have come like to this point right here before it backtracked. But um, because this wall right here would have been blocked by other obstacles, so it probably would have seen this as a potential gap until it got to that point. So, but because the viewpoint is so small, it had to basically get to this point right here before it could kind of see the fact that everything was kind of cut off to them. So it goes back to the next nearest point, which is right here, and it will, go on down, learning as it goes to basically this point here. Um, it looks like it tries to turn this way first and sees that there's a wall there with, kind of a negative backtracking. So it kind of turned right back around and tried to go back up this way. Sees the wall there, continues moving on up. Now, personally, I don't know why it continues moving on up when this right here, this particular gap, still has a higher or a lower distance value here than it would say up there. This right here is closer than say way up there. So I don't know. But it goes along here, tries to find, trying to find gaps, um, and gets to this point and says, "Hey, we're gonna like continue moving up this way," and it finds out that everything's kind of pretty much blocked. So it traverses back on down. Um, so see. Hmm. Hmm. Okay. Hmm. 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 Don't know why it included 4 blank pages, but whatever. PowerPoint, huh? Oh, wow, that is a huge PowerPoint. Okay then. Let's see. Let's see. Informed search. No information obtained from the environment. Blind search. Informed search. Use evaluation function. More efficient heuristic search. That's the problem. We don't have a. Our search isn't really all that informed. So okay. To list to store information about nodes, open list stores nodes for expansions, close list stores nodes which have been explored. Let's see. Dice search. 2 examples of running A star. So, okay. Let's see. Expand the start node. Okay. This is obviously weighted, so they're basically saying, okay, this is the cost of going to A is 4, 3, and 1. Cost of going to C is also 4, 3, and 1. And the cost of going to B is just 3, 2, and 1. Um, so you basically add those um, into the queue, trying to find the lowest, fastest path. So you're basically putting, B in there first, and then you can put in, A and C, or you can put C and A. It all depends on how you kind of code up your project. So, um, okay, so it pops off B. So then it kind of sees the fact that you have G, H, and I there. So it starts kind of adding these values in. So H has 2, which is interesting because they're kind of making this equal to 3. So, hmm. I love it when my headset shuts down on me. Music, I need you in the background. Go. Wasn't paying attention to that. Okay. Um. So let's see. Not quite sure why they're putting age is equal to 3 on this because um you would you should be like adding all of these into one particular value. It's not like you're taking edge, edge, and then value there to get to where you're going, or node and node. So I don't know. I would figure that H would be more 5 than 3. You still have A is equal to 4. You still have C is equal to 4. Then you have I, which has 4 there and 3 there. So that should be 7. Don't know why it's set to 5, but whatever. And G has 6 added on there, plus 3, so that should be 9 to kind of get to G there. Um, because you're adding on the cost of, moving from your start node, through the edge and the vertices here to kind of reach your goals here. Um, so the next set should technically be um, A and C. Um, but they're saying that H is the one. But as you can see, H has no expansion. There's nothing connected to H that you can kind of move on to. So we're blocked. We can't go any further than that. So we don't do anything. If there was a path to say, H to G or H to I, then obviously it should be able to continue for the most part to see whether or not this route here is going to be faster than that route there. So if it's like this and that is faster than that, then you can test to see whether or not that path will work. So now we go to A's 4, and then we look at E, D, and F. So um, again, E is showing the fact that it has node, edge, and edge for a total of 3. Um, that's what they're calculating it to be. Um, yeah, it looks like they're just kind of calculating the edges to get to set goal because they're saying that the goal is 5 distance altogether. So, um, but basically you look at A and you know, you add in D, which is they're calculating it at 5, so edge, edge, and node. And they're putting in E, which is edge, edge, node, so that's 3 for E. And then for F, they have 3, 6, 7 for F. So um, you still have C4 here that could potentially be closer to the goal. overall. Um, so, but um, see, like for example, the cost of the path to get to the goal through C is actually shorter. So 1, 2, 4 versus 1, 2, 5. So, um, so it's not always the quickest path, or it's not always the best path to kind of, um, especially if you're dealing with weights along these lines. Okay. Um, Now, if it was non-weight, then you'd have, you know, this node added into your your path in here. And for A, it would add in, you know, D, E, and F. After B and C, you would check out B and see that there's G, H, and I, so that adds on into the stack. And then you have C, which has J, K, and L added in. So then it goes D. No, doesn't have anything D. E. Oh, that has a path. So you could pretty much go with that route if there was no weights whatsoever. So um, there might be a shorter path, but assuming non-negative arc cost, nodes with a lower priority than the goal cannot yield a better path. Okay, understood there. So basically, they're stating that because you have, 1, 2, 3 to the goal, the ones that have like 1, 2, 3 for D and I, F, and G are, um, you don't need to worry about. You can just kind of pretty much say you're not going to get the best path on this whatsoever, no matter what. Um, see the path here would be, 1 and 5, and it hasn't even gotten to this point yet, so it's already this route right here is already equal to this route here getting to the goal. So, you know, this route isn't going to work. Um, Now, the fact that you have, you know, this equaling 5, uh, that shouldn't really matter all that much if 3 here is, equal to, say, just if it's just 1. If the edge is 1, then um, you might be fine. You might be good on that because, you have 1, 2, and 1. That's shorter to get to the goal than, your initial route. So, um, so I would almost say the paths that have like the 5s might be perfectly fine. Might be able to kind of get you to where you need to go. Um, it all depends on the edge cost on there. So, um, the fact that the edge cost to get to G and F well, to G in particular is equal to 5 is not going to work. So that's a deadline right there. Okay, you're not going to be able to reach the goal any less than 5. Um, the fact that you have 4 here for F, I mean, you would need an edge of 1 from F to the goal in order for it to be equal to, the AE line. Okay, so not exactly looking good for F. Definitely G is out. Um, I still has a possibility. Um, D also has a possibility. So it should probably still kind of test those out to see if there is an edge, from D to goal, for example, that's equal to 1. That would be a lot shorter than what you have, 3, 1, and 1. Um, same with I. So, so they're already kind of talking about how, C, you have K, L, and J. Once again, these are equal to 5, but again, their paths, the edges might be something that would work for the goal as well. I mean, J might have like another edge to goal that has this a weight of 1. So, um, so this isn't exactly ideal. So, I'm busy phone, go away. All right. Um, okay, so we are trying to get from A to N. So now this time we are okay. So we have the weights of each of the nodes in particular. So, A has a weight of 14, B has a weight of 10, E has a weight of 8, and H has a weight of 8. So then you add the edges to the the weights for each one, and you have, you know, E is 8 plus 3, so that gives you 11. B is 4 plus 10, so that's going to give you 14. And you have H, which has 8 plus 6 is going to be equal to 14. So it looks to E first. Um, so now from E, it checks out, these other paths here. Now, the yeah, so it checks here that A to E to B, you have a path of 6 plus B is equal to 16. So that's not a great path. So it pretty much ignores this one and removes it. Doesn't want it. Um, it looks to this path here. 3 plus 4 plus H is going to be 15, which is more than the previous version. So we can basically ignore both of those. But we have two new nodes here. We have I and we have F. So I will get the 5 on its node, and it's going to look at just the edge cost. So 6 plus the 5 will give it the 11. And F will have 3 plus 4 plus F itself, which is also 7. You're going to get 14. So you have 11 and 3/14 there. So we look at the next best one, which is I. So um, so now we look at the cost of going to I plus the cost of going to H. So 6 plus 4 plus H is 8. So you get 18, higher than 14, so we don't need to worry about that. Uh, we have F here, so 6 plus 4 plus F. So you got 10 plus 7 is 17. That's greater than 14. Don't need either one of these two. So now we look at all the new nodes that we haven't come across yet. So we look at, we'll look at J first here. So we have 6 plus 4 plus J, which is 2. So that's a total of 10 plus 2 is 12. M, we have 6 plus 4, that's 10, plus M is 2. So once again, that's 12. So those get, bumped up to the very top there. And you have L, which is 6 plus 3, that's 9, plus L is 6, that's 15. There you go. And it gets put at the very end. So it picks um, it picks the first one on the list, which is J. You know, uh, you could um, you're when you're selecting the nodes, you can pretty much have the kind of computer select whatever it wants. You can kind of have it do it random. You can have it you can select like a left to right process or right to left, left to right or right to left. You can do it random, but one way or another, you're going to need to visit each one of those nodes no matter what. Um, so, um, so it looks through this, goes to J, picks J as the path, which is a total of 10. So here we check to see whether or not we have anything faster for M and F. So you have 10 plus 4, that's 14, plus the cost of M is 2, that's 16, greater than 12, don't want it. So we check 10 plus 4 plus F, which is 7. So you're talking 14 plus 7 is 21. 21 is greater than 14, so we don't need that path either. So we look at all the nodes that we haven't seen yet, which is G, K, and N. So let's look at G first. We have 10 plus 3, that's 13, plus G is 6, that's 19, so there you go. Gets put at the very bottom of the list there. look at k. So 10 plus 4 plus k is 2. So 14 plus 2 is equal to 16. Not that much better. So now you look at n, which is 10 plus 3 plus 0, because that's our destination. Um, so you're looking at 13 on here. Well, we might be, um, we might have a faster route, going through the M route there. So it checks out the M and checks to see whether or not um, its distance to N is shorter, to the other two nodes there. So it it goes the 10 plus the 4 plus the N, which is 0, so that's 14, not greater than 13, so it doesn't have a better solution to that. And then it checks to see whether or not there's a solution for L. So there's 10 plus 4 plus L. That's a total of 24 in this particular. Oh, wait. That's not 24. What is it talking about there? That's um, 3, 6, 10, 14, because it's coming from M, and then L. So that should be 20, not 24. I don't know why they have 24 there, but their math was off on that. So, and obviously the path getting to L was faster, you know, previously, um, just by going from I, for example. So, so obviously M doesn't help out L whatsoever on that. So, um, it's noticing the fact that n of 13 is the quickest way there. Um, so that's the route that you would take with A star. Um, I mean, you could check out these others, but it's not really worth it because the cost of these other paths are greater than your shortest path. So it doesn't really work out. You just want to kind of stick with what you've got. So you want to kind of stick with your lowest path, your quickest path. So um, so let's see. A star replanner, unknown map, optimal, inefficient, and impractical in expansive environments. The goal is far away from the start, and a little map information exists. Now, this is something that I'm probably going to be trying to work towards on my particular map. So that's why Steins came in with the dynamic A star search here. So benefits optimal, complete, more efficient than A replanner in expensive and complex environments. Local changes to the world do not impact on the path much. Most cost typical remain the same, avoids high computational cost of backtracking. So um, X and Y states of a robot, back pointer of the state X to the next state Y, arc cost path from Y to X, arc cost of the path from Y to X based on sensor, tag new open and closed of the state X, path cost, and smallest value of heuristic X since X was placed on the open list. Robot moves in 8 directions, our cost values. Okay. Let's see. Okay, it's giving all the pseudocode, which is good. That's helpful. But I kind of want to see it in action a little bit. Much like how you have the examples up here. I want to kind of see how it kind of handles that same kind of process. So let's see. Okay, so here we go. D-star example 2 out of 23. Initially, all states have a new tag new. All H and K values must be measured as distance in grid to goal. You have clear versions here. Not knowing what's there, you have your initial goal, you have your start, you have obstacles that will cause problems, and you have a gate. I'm not quite sure why they have a gate there, but whatever. Okay. Put goal node into the queue, also called the open list, with H equals 0 and K equals 0. K value is used as the priority in the queue, so initially this looks like Dexter's search. So, um, okay, so pop the goal node off the open list and expand it so that its neighbors 6, 6, 6, 5, and 7, 5 are placed on the open list. Okay, so it's it's adding these values, to the open list. The um, so now um, you have closed and currently being expanded, and then you have like permanently closed. Okay, so hey there, Seth. How you doing there, bud? Welcome back to the stream. Okay, so um, if Cole is equal, then each neighbor of y of x, if t of y is equal to new, or b of y is equal to x. Basically, general checks to see whether or not the values are, you know, something that could still kind of work for you per se, but um, seeing that these haven't really been looked at, they're um, they haven't been looked at before, so that you can basically state these as um, as new values. So now um, the each one of these nodes has an h and k of 1 based off of the distance from the goal. And then, of course, you have the where you kind of came from, seeing that the this particular node is from 7.5. You know, this is basically stating uh, where you know it was put on the stack from this particular node. So it kind of it gives you a path back to that one that just kind of got popped off. So all these kind of get placed into the stack, into the queue. So um, so now you look at the values here. Um, so okay, I see what's kind of going on. The distance from the goal is a little bit different for 5.6 because it's or 6.5 in this particular case because the distance is a little bit further from it. It's not just like a straight line. It's um, hypotenuse. So the distance is a little bit further from center point to center point there. Not as, you have a shorter distance for this one and that one. That's why you have, the K values of 1 and compared to the 1.4 on that. So now the 7.5 and the 6.6 values there, you could have put either one. They are both literally the same kind of node. So you could you could just kind of throw one over the other. I mean, you really don't know when it comes like to like pathing at all. If you're not totally aware of what's going on, then you know left right you don't really know. So you basically say, okay, I'm just going to throw the left one on there first and then the right one. You could throw the right one on there first and then the left one. Doesn't really matter. That's based off of you as the programmer. You could um, set it up so that the computer could try to learn, um, what kind of, um, you could try to see what you can try to set up your AI so that it could try to like learn over time. But I mean, for this particular game, I don't really need it to like learn over time because I mean, when they shut down the game, all that information is gonna kind of go away unless I store that information in a file that it can access a little bit later so that I can keep on referencing it back. I could do that, but at the same time, um, that might be for like a maybe like a later project, like a project number 4, like GGG 2 or 3 or something like that. I could try to maybe do more of a learning AI so that it understands, hey, um, it's its decision whether or not it wants to kind of go left or right. Maybe it finds that going left is a little bit better than going right. I don't know. But we can always kind of work on that later if we really want to. But for now, we're just gonna, kiss it, keep it simple, stupid, and move on. So, um, So we have our two nodes here that are pretty much exactly the same. So we go ahead and pop one of those two off here, and we look at the values um, from that. So we look at the distance here and notice that the um, we're still adding like a single digit value to these. So you're just looking at 2 and 2 there. This this is the where um, it got spotted from 6.6 in this particular case. So and then it checks out this node here, which is again within its kind of uh, line of sight, the potential destination. And once again, you add the distance here and the distance there, the lengthwise. So the 1.4 as you know, so you get the 2.4 on those, which gets placed on the stack there. And then of course, where it got spotted from 6.6. So um, so we can see that it is closed, but it could still potentially be worked on a little bit. It's um, all the nodes around it um, haven't really been closed, I believe. So that's probably the reason why it hasn't been completely closed off yet. So that's what I'm imagining, but I could be wrong on that. So now it goes to the 7.5 and pops that off. So, or at least it should. It should be going to that one next. And I was right. There it goes. Um, okay, so once it once this one got completely evaluated, it found all the nodes around it and so on and so forth, it got closed off. It was like, I'm done, don't need it anymore, so we're gonna move on. So now we look at this and evaluate everything that is associated with that. Now, um, it may look to this one here, which is, distance of one, which doesn't really work for this because it's a 1.4, not a 2. So this node right here isn't going to change. It's still being evaluated from this, the 7.6, not the 7.5. So there's nothing to be changed there. So now it looks at these two nodes that are next to 7.5 and gets the distance and evaluates where it came from. So um, now if this was being done with um, bidirectional here, then um, you could be seeing the exact same thing happening from this node over here as well. You know, you could have done, say, uh, from this you don't really have much, but you know, you have this point here could have been the exact same thing, done for the open or for the start node. Um, and after you get done with this, you still had this to be also be evaluated as well. So, this one could have also had the 0 0 and b is equal to nothing. Um, and then you could have evaluated all these three around it to see if um, how good of the distance it is from there, from this particular spot. So, and then, added it to, your list here, which, you would have had these two with ones, and you would have had, these three as well, added to this particular list. So, um, and then as you would have had like the 1.4s here as well. So you could do that. Um, but you have the 1 and the 1.4 and the 2 and then the where it came from. So now we move on to the next one. So which would be the 6 point, and the 6 and 5. So this particular node would be going next. Oh, they seems to have jumped a little bit here. Interesting. Um, Interesting that they kind of jumped a couple steps here. Let's see. But I mean, it still kind of explains um, kind of the process of going one by one through this. So they definitely kind of skipped a few steps to kind of get to what we have here. So as you can kind of see, the distance is kind of reflective of what's kind of going on there. So you have 3 and 3, 3.4, 3.8, 4.2, 3.8, 3.2, and or 3.4, and then the 3 and 3 there. Um, so um, so it's looking at the 4 and 6 and notices the fact that you have you know spots that are just super large. The obstacles, you want the values to be super extreme. So um, you know you can still kind of add them to the stack, but they will never be evaluated. So they will never, you will never get to a point where um, you've ra- um, run out of spots to check out. Or if you did, then you basically have no path from the start to the goal, which means that it's, my AI agent would need to basically continue kind of going back and forth along um, the obstacles to wait for a path. So, um, or it basically kind of stops at the closest spot that it can kind of get to and just kind of wait there until a path kind of opens up for it. So let's see. Okay, so once again, they jumped once again all the way over to here. Um, Now, if we did like a bi-directional, then it probably would have evaluated all these nodes, to be honest. Um, but it might have found a path that might have been a little bit short. It might have. Well, it might have been able to kind of figure out where to kind um, it might have evaluated a little bit more. Well, I mean, all the nodes would have been evaluated at, one way or another. Um, but problem is that this isn't like showing the amount of um, potential steps here. So um, okay, so somehow you're able to kind of get through the gate on that. I don't know what they meant by the whole gate being a thing, but maybe it's just something that can kind of be opened up or something along those lines. Don't really know. Um, they didn't really kind of um, expand on that really. And they're not really saying anything concerning the gate at all on that. Um, so it finds the optimal path from start to goal. Um, okay. So here they're talking about how the robot is starting to move from this point to that point, and then it tries to go to this point here and finds the gate. Okay, the robot starts moving along the optimal path, but discovers that pixel 4.3 or 4.3 is an obstacle. Okay. Increased by a large number. Transition cost 4.3 for all nodes adjacent to 4.3. Next, put all nodes affected by the increased transition cost, all 9 neighbors on the open list, including 4.3. Note that some neighbors of 4.3 and 4.3 itself have lower k values than most elements on the open list already. Therefore, these nodes will be popped first. Okay, interesting. So it's reevaluating itself again from where it was to it's restarting the process of popping everything off right at the moment. How is this faster? See the oh wait. Okay, hold on. Okay, I see what's going on. So because um, it started moving and it went to this particular, it was trying to get to the goal, so it was moving in a straight line, and for some reason they didn't count gate as an obstacle. Again, I don't know why um, they did it that way. I mean, if it can kind of see um, if it can kind of see the gate, then it should know that it can't get through it. So it should automatically say, hey, I can't see it. But um, at the same time, well, okay, here, let me kind of let me try to explain this a little bit better. The there's a reason why like the bidirectional might have kind of helped out in this particular instance here. Um, the um, if it's well, here's what I'm having a problem with. Okay, if it can see that these are obstacles, then why didn't it consider this an obstacle initially? Okay, why didn't it consider the gate an obstacle? If it already sees these as obstacles, why didn't it consider the gate as an obstacle? Why did it even consider this as a spot to actually go to? That's why this particular example is kind of confusing as to they even why they even did this. You know, if they're already seeing these as obstacles, why didn't they consider this as an obstacle as well? Because it's something that the robot can't get through. Now, if it was something that could get through it, meaning that it was an obstacle that the robot can't get around or find a way to get through it or something along those lines, and that's great. But um, if you know ahead of time that the robot can't get through it, then like for example, if I see um, if I see like a building that I'm walking up to, okay, and there's a door there, okay, I don't know whether or not the door is locked or not. If I have the key for it, then it's not an obstacle, okay? Um, but if I don't have the key, then it might be unlocked and it might not be unlocked. So it could be something that you can kind of pass through. So then I could probably understand a little bit this particular check on that particular gate. Is it something that you kind of get through or not get through? Is it locked or is it unlocked? You don't really know. Um, but um, if you know that your robot isn't going to be able to get past it, meaning like um, it doesn't have the necessary um, tools at its disposal to be able to like open up a gate, then it should automatically see the gate as an obstacle, something that I can't get through. If that door's if if you can't turn the handle to a door, then that's an obstacle. You can't get past it. So best to kind of treat it as an obstacle. You know, don't allow for it to kind of get through it at all if you already know that it's going to be a problem. So, so that's why I'm kind of curious as to their their reasoning behind this. Hmm. But this might actually be somewhat useful for me in a sense that um, okay, so let's kind of put it this way. Um, we have our start and we have our end goal, right? Okay, we have, where our AI agent is going to start at, and we have where the potential goal is located at. Now, um, so here's where things get a little tricky here because um, if I'm going to be putting in like a fog of war or something along those lines, okay, then its area of viewing is not going to be that large. So, um, so I'm not going to be able to do a proper like A star all the way around. I'm not going to be able to um, do okay, so for this kind of a map, everything is known to, everything is known to the like the map maker, everything is known. You see where all the obstacles are at. You see where, you see the path from start to end. But if we put in like a fog of war where you don't know row 5, you don't know row 6, you don't know column 6, you don't know column 7, then you might be kind of looking at all of this and going, okay, well, I'm going to have to kind of, you know, expand out the search from only this point to get to, you know, obviously I'm still having a point of destination that I want to kind of get to, and I need to kind of go in that general direction. But um, it's going to get to a point where it's going to like look at this node here and this node there, see that they're kind of equivalent, but it's going to wonder, which of those two directions do I go? So, hey there, Jedi. Um, no worries there, bud. No worries. So, it's not quite the same in terms of, hey, this this particular node here isn't the exact same as this in terms of distance, because this is going to be like 1.4, 2.4, and then 3.4, for example. Um, Whereas this one is going to be, 3 and 3. Um, so this one would kind of get popped off first. And by that point, you have more of a vision of the map being seen by the player. So you'll know, pretty much all of row 4 at that point. So now seeing that this is like the closest um, spot to the end goal, um, you can continue kind of working towards that. Now, if um, if say these particular nodes gets blocked off, for example, okay, and it sees that, then obviously it's going to need to kind of walk right back over here to 4. Um, but this is going to be requiring um, these values to kind of stay within um, to kind of stay with that agent at all times, so that it will go, okay, well, I can't get to where I need to go from here. you know I'm seeing these as barriers here that I didn't see before. So now I'm going to need to kind of go from this point here, walk back to this point, you know, and um, see if this point can kind of get me to the end goal. So, um, and if I can't find a path, then it's probably going to have to kind of go back and forth between these two spots and go, what's going on? um, but that will probably mean that I'm going to need to kind of hold on to these different states each and every single time. Um, and it might need to kind of reevaluate to try to get back to like this point here. But with the, when you find that these are blocked, then all it means is that it just needs to kind of backtrack back to its original starting point and continue back, going along the new path. So, um, so again, I don't know whether or not, um, the whole, I don't understand them like going back and kind of popping off these 4 nodes here and evaluating all of these heuristics again in this particular case. See, 5-4 is popped first because its k value is smallest. Since its k and h are the same, consider each neighbor of 5-4. One such neighbor is 4-3. Right. 4-3's back pointer points to 5-4. But its original h value is not the sum of h4's h value plus the transition cost, which was just raised due to the obstacle. Therefore, 4-3 is put on the open list, but with a high H value. Note that since 43 is already on the open list, its K value remains the same. Now the node 43 is called a raised state because H is greater than K. We pop 5-3, but this will not affect anything because none of the surrounding pixels are new. The H values of the surrounding pixels are correct. A similar non-action happens for 4-4. Okay. Pop 4-3 off the queue. Wait. Pop 4-3 off the queue because K is less than H. Our objective is to try to decrease the H value. This can defining a letter path from 4-3 to goal, but this is not possible because 4-3 is an obstacle. For example, 5-3 is a neighbor of 4-3 whose H value is less than 4-3's K value, but the H value equal to the H value of 5-3 plus the transition cost. Therefore, we cannot improve anything coming from 4-3 to 5-3. Note that we just assume all large numbers to be equal, so it's equal to that. This is also true for 5-4 and 4-4. So we cannot find a path through any of 4-3's neighbors to reduce H. Next we expand 4-3, which places all those pixels back. These back pointers point to 4-3. In this case, only 3-2 on the open list with a high H value. Now 3-2 is also a raised state. Note that K value minimum of its old and new H values. The setting happens in the insert function. Next we pop 5-2. This will not affect anything because none of the surrounding pixels are new and the H values of surrounding pixels are correct. Okay. Pop 3-2 off the stack since K is less than H. See if there's a neighbor whose H value is less than the K value of 3-2. There is, we'll redirect the back pointer through this neighbor. However, no such neighbor exists. So look for a neighboring pixel whose back pointer does not point to 3-2. Okay, so there's only one. Whose H value plus the transition cost is less than 3-2's H value, which is on the closed list, whose H value is greater than the 3-2's K value. The only such neighbor is 4-1. This could potentially lead to a lower cost path, so the neighbor 4-1 is chosen because it could potentially reduce the H value of 4-3. We put this neighbor on the open list and its value H value. It is called the lower state because H is less than K. The pixels whose back pointers point to 3-2 have an incorrect H value, and H value neighboring pixels not equal to the H value. Put into priority queue the maximum H values, making them raised states. These are 3-1, 2-1, 2-2. Note that the K values of these nodes are set to the minimum of the new H value and the old H value. Okay, pop 4-1 off the open list and expand it. Since 4-1's H and K values are the same, look at the neighbors whose back pointers do not point to 4-1. See if passing through 4-1 reduces any of the neighboring H values. This redirects to back pointers are 3, 2, and 3, 1 to pass through 4, 1, and then puts them into the priority queue because 3, 2 was closed to its new k value is smaller of its old new h value since its k is equal to h. It's now a lower state. Okay, pop through one off the list. Since k 6.6 is less than 7.2, ask is there a neighbor whose h value is less than the k value of 3, 1? Here 4, 1 is. At the transition cost of 4, 1 and the h value of 4, 1 is less than the h value of 3, 1, then reduce the h value of 3, 1. Or this is not the case. For Q, so K becomes a lower state. I don't know about this. Hmm. Focusing heuristic being an estimated path cost from road location R to X. Estimated path cost. Let's see. Hmm. Two estimates of cost per node. Um, Distance, no back pointers. Right edge from node A to node B in the graph. A is a successor of A is a predecessor of B. Hmm. Okay. Open list. 0, 0. 1, 1. Okay. One, 1. Infinity to 1. Add those two in. Check this one out. Find that we can't find any vertices around it that we can get to. So now we go to this one, 2, 2. Add these two in. Pop this one off. I have 2, 2, or 2, 4, 2, 4. Add these in. So it's gonna go back to this point there. Finds 3, 3. Doesn't find any additional nodes. Doesn't have any way to expand on this particular node whatsoever. So that's where that ends. Now this one was found first out of these two, so this one's going to get popped off next. 3, 4, and 3, 4. Once again, finds no, doesn't find any faster paths for either one of these two. So like, the 1.4 doesn't increase there, and the 4.4 doesn't increase there. So that one's done. So now it's going to pop that one off. And then it's going to find these three nodes. So then it's going to pop that one off. Not going to find any good spots or anything good to kind of change on those. So we're going to go to this one now. Yep. Which then it pops all those. Now it's still going to pop these two off first, or at least it should. Yeah, there goes that one. And then it'll pop that one off. This doesn't change these values there, so pops that one and adds those two into these, which it does. And then it goes to the next lowest one, which is the start there. And obviously the other values are not going to be lower than what you find there, so you're pretty much done. You found your goal. So suppose that in trying to move from 3-2 to 2-2, the robot discovers that 2-2 is actually an obstacle. Now replanning is required. Okay. Again, I don't know why you're seeing obstacles here, but this suddenly become, you didn't see the initial obstacle when you did the planning for this already. So that's why I'm kind of confused about why they throw this in saying, hey, this is now an obstacle. So okay. Okay. Interesting. Now this might this might be good um, in that, if obstacles do pop up, then it might be a good process to kind of do a kind of a refactor of it. Um, but at the same time, if this is kind of guessing as to whether or not you know the full map or whatnot too. So it's stemming from the goal. Saying, hey, here's the goal. Here's the path. You know, from the goal. Um, it really should kind of start um, from where the agent is, um, and it should kind of um, go each. In my particular example, it needs to kind of go check the surrounding area. Don't go towards the obstacles. Go towards the paths that are, you know, technically closer to the final destination that you actually kind of want to get to. So you kind of go in that kind of general direction um, until you actually kind of get to the goal, by the roundabout way of it. Um, so I don't know. I don't, I mean, I do appreciate the overview of the algorithm and the examples on this PDF here. This is a really good um, showing of what you're going to be kind of facing with D-Star. But I don't know if it's something really um, that I really kind of need for this. So I'm kind of looking at this and going, I don't know. I don't know if D-Star is going to be good for me. So let me make a note of it. Um, um, the fact that it tries to get the tries, tries to get the full path from the goal to start um, doesn't really help for my particular game. And what I'm going to do is I'm going to go ahead and save this PDF though, because this was a good PDF. I like that. I like this. So we're going to go ahead and save it to my information here. Um, let's see. Good PDF of information. Um, Pseudocode and examples. Yeah. So if I look at these others and I find that out of them all D-Star still kind of works for me, then we'll kind of fall back on that. Um, I get I get the idea of it being dynamic, um, which kind of helps. Okay, so let's kind of do it this way. If let me kind of point out why D star is a little bit more efficient than A star. Let me let me let me bring that out there. Okay, so let's go back to the PDF here. So we'll go back to the non-delight example that was up above here. So if it finds the gate to be an obstacle, right? It's probably it probably didn't know that the gate was an obstacle kind of thing. It might have like looked at it and seen this is a wide open space, even though technically there's something there that could cause some problems with me. Um, then um, once it got to this point here, it would need to basically redo all of this work here from the goal again, for an A star. It would need to kind of say, hey, this path doesn't work for me. I need you to do another A star from the goal to its stopping point, which is right there, which isn't that isn't that much. Which means all these steps, all these states that it's going through, it has to kind of go through them again to get to the start, you know, to get to that start node. Because it's no longer here anymore, it's there. So, and now you're redoing all that work, all those algorithms to get to this point. So, um, so instead of getting to kind of like this point here, you would kind of get to like that point, the column three for the most part. Um, and that's a lot of steps. Now with the D star, it's saying, hey, this potential path that you wanted to use is now an obstacle, so we're gonna have to kind of go and look at the other um, potential spots and see if there's a way to kind of get around it, or it might need to just kind of see about trying to find the other paths, from that kind of list. But all this information still needs to kind of stay with that particular agent, you know, until it reaches its goal. So all these queues and like, all these lists and storage is going to have to kind of stay for each one of the agents in order to find the next best path. So it might. So you're looking at uh, a potential cut down on the amount of runtime trying to do the A star over and over and over again. Um, but you're adding to the overall storage because each one of the agents is going to have to kind of keep a hold of this information as it's moving along so that it can redo, it can kind of handle the D star, and try to reevaluate where it should be going. So, So it's good, you know, in that you don't have to kind of redo the A star over and over and over again, but it just means a little bit more storage for each of the AIs. So, so D star is better, especially if you know, it's it's meant to be a dynamic A star. Well, it fits. It fits that, so it works. So I could see why. Now it's going to be more code as well, but again, um, more code, more storage, but at the same time, you're looking at um, a little bit more of an improvement overall with A star, especially seeing that it's dynamic. So, um, so yeah, this is good. Let's see if there's something a little bit better though. So, um, this looks like it's the original um, PDF from the yeah. This looks like the same kind of PDF as this one, although not quite. Boy, these look awfully familiar, awfully close to each other. All right, we'll go ahead and close off all these. We don't really need them. All right, so now let's we took a lot of time on D star, so let's go ahead and um, let's kind of look at the jump point. I don't think I'm going to be using it because it's saying that it kind of jumps a couple nodes, um, and I don't think that's going to really work all that well um, for what I have. So, but we'll check it out anyway. So, jump point algorithm. Okay. Okay, we'll go ahead and open that up just to kind of show what it's all about a little bit. Um, we're not dealing with a sorted array, so that doesn't really help us in that. Um, it's talking about a lot of um, it's talking about a lot of sorted arrays and stuff like that, and it's just not what we need. Um, let's see, jump, search. Hmm. Okay, well, apparently I can't get there right at the moment. That's unfortunate. Geeks for Geeks is something that I can't reach. Okay. Hmm. Search, maybe pathing. Let's see. Okay, let's look at this a little bit. How to speed up A-star pathing with a jump point search algorithm. So it's important to understand implications. Um, this implementation is based on an original paper and article on GPS found here. Jump point search. The Lua-based implementation jumper was used for help with some parts of the implementation. Um, no Flash. Check out that, Flash kind of got removed, so hmm. Eh, Um, Pathfinding is often used in video games. You should be sure to bump into it at some point during your game development career. Yeah, pretty much. It's primarily used in to give intelligent looking movement behavior to artificial entities and PCs to avoid them bumping into things, often. In some games, player avatar is also subject to pathfinding. So you might assume that the problem is pathfinding is solved, but unfortunately that's not the case. There's no silver bullet which you can use and just be done with it. And even in triple A games, you will still find funny things like this. Yep. Hey, Thin. Thanks for reading there, bud. I appreciate it. How you doing today? What were you working on? Okay, so we are currently looking at jump pathing right at the moment. So how's pathfinding going? It's going okay. So right now I've narrowed down my, last week I basically did a overview of, a lot of the different searches that were out there. You know, uh, if you go to like the Wikipedia page, you'll see multiple different searches. Here, let me, you know, uh, for anyone that is curious. So, so you have quite a bit of listing of graph and tree search algorithms here. So I basically took the time last week of, going through each one of these and kind of showing why they're not going to be like working very well for the game, my particular game, but at the same time, they might still be worthwhile for someone else's game, for example. Some pathfindings, they might actually have, um, travel time, travel distance, um, difficult terrain, or something along those lines, something that can add to the overall difficulty of the pathfinding. So, um, you know, weights from the nodes and the edges might be something that, someone else might be tackling. But for my particular case, I'm not going to be doing that for this particular game that I'm working on. So I don't need to necessarily worry about that. Now, maybe, when I get to like version 2 or 3, later down the line, I might consider adding on some like difficult terrain or something like that. Maybe something that I'll have to kind of think about at that particular juncture. But um, and I'm already familiar with A star, but I saw that some of these algorithms were saying that they were a little bit better on their A star. See, the D star here was saying that it was more efficient than repeated A star searches. I'm like, okay, that's nice, that's good. Jump point preserves A star's optimality while potentially reducing its running time by order of magnitude. That's good. That could be helpful. French search does 10 to 40% performance boost over A star. Okay, interesting. And then of course we have um, LPA A star, which was uh, it was basically storing the A star search so you didn't have to redo the A star over and over and over again. So, um, so it was definitely something that uh, for this one in particular, you have it store the A star search once for your map, and it's all done. Now, obviously, that could be really difficult depending on the game that you're coding up, you're developing. If you have like a small map or a small screen or something along those lines, then you don't necessarily need to worry too much about it. But when you get into something that's um, extremely large, such as like like a World of Warcraft map or something like that, it's like yeah, you might want to reconsider uh, using LPA for example. But um, you were working on sprite art today. Nice, nice. Yeah, um I was I'm not an artist whatsoever, but I don't have anyone that I can well I couldn't pay anyone to do any kind of art for myself, so I did my own art for it, and believe me, it looks it. So, um here. Matter of fact, let me go ahead and kind of um, show you what I got for that. So um, now, with Unity, there's free assets that you can get to use if you want to. There's also some like additional like art um, pieces that you can kind of purchase if you want, if you have the money for it. Um, but some of the um, the free assets weren't really looking um, exactly what I wanted, or exactly what I want for the game. So um, I decided to try to put my own hand into art creation, and well, it's pretty bad, but okay, what's going on here? Unity is taking its time on loading that, apparently. Okay, so, um, well, while it's thinking, oh, there it goes. Now, the tiles themselves are something that I got from okay, there we go. The tiles themselves were art assets that I got from the free um, asset store, but these particular characters there, those are ones that I generated myself using vector graphics. Um, so, but we're gonna kind of continue working on. Uh, we're just kind of making sure that these characters can kind of walk around the map, um, with little. Well, I mean, so the purpose of this game, um, I don't know if you've played Majesty before, but in Majesty, the player doesn't directly control the units. The units are kind of going off and doing their own thing. Um, you have them kind of acting and reacting to certain situations in that game, and the player themselves are basically saying, build here, explore there, hunt this, and that's pretty much it. While just kind of purchasing additional heroes, building the buildings and so on and so forth, upgrading everything. Um, so I kind of like that mentality of, um, while the player might be somewhat in control, they're not totally in control. So, um, so I'm kind of trying to mimic that kind of same style in this particular game. So, but we need to figure out their pathing so that we can get them to be able to kind of walk around the map without too much difficulty. Obviously, we're probably going to have issues where, um, you know, things like this are could potentially be a problem in my game. But obviously, I'm going to try to work on making sure that something like this doesn't really happen. But, let's face it, not everything works out perfectly. So, um, so we're gonna continue trying to research jump search right now to see whether or not it might be a good alternative. So far, in, you know, I was impressed with D-Star. Um, in that, you, if you know the D star basically stands for dynamic A star, meaning that if there is a change in the path, meaning that there's like an obstacle that just suddenly appears in the path that I was trying to take, then it checks to see whether or not there's a way around that obstacle, using the information that it was already kind of there. Um, the This particular PDF here was pretty useful um, when it came to kind of getting the examples of a um, what the D star is all about. So it skipped some steps, but I mean obviously it was already kind of it was kind of already showing the algorithms as it was anyway. So, and then it shows, hey, here's your robot moving from the start to the end goal, but it encounters an obstacle. So now it has to try to refigure out how to get around the obstacle. So it's interesting, and it might actually work fairly well for my particular game, seeing that while one of the agents might be walking to its particular destination, another agent might be saying, hey, we're going to put a barrier right in this one agent's path. Um, so this agent might now need to kind of move in a different path. So D-Star is looking good, um, but at the same time, I can't do um, I don't want to have like a full A star, like, um, I want, the idea concept of it is to do a fog of war, which means that um, they're not going to know the full map, or the AIs aren't going to know the full map, so they're going to be kind of exploring quite a bit. So a lot of backtracking initially until they kind of get a relative sense of where everything's at. So, um, I don't like those AIs that, go, that sees the full map, you know, and goes straight for you. Like, I'll take, for example, say, like the old real-time strategies of like, Warcraft or StarCraft. The AI opponents, they don't really explore the map. They know exactly where you're at. So they'll beeline, they'll build up their army and go straight for you. There's no exploring around trying to figure out where they, um, where your opponent is on the map or anything along those lines. It knows where you are at, so it goes straight for you. I I don't really like those kind of AIs, that sees the entire map and goes, "Oh, you're over there." So don't like those kind of cheating AIs. So I'm trying to build this so that doesn't have to work that way. But we'll see what happens. So, um, see, A star pathfinding refresher. Don't need to worry about that. Um, Now, um, if you have any kind of questions about pathfinding, like if you're not quite sure about A star or what it's all about, then feel free to ask questions if you're curious. Um, so, or or if you have any kind of experience with any of these other um, yeah, algorithms already, then go ahead and put them in the chat. Let me know. Uh, I'm, I welcome any kind of input that you might have on this. So, or if you have like any kind of like good like resources or like videos or something along those lines, um, then go ahead and put those in the chat as well, you know, and I'll check them out at some point. I need to learn it because I'll be adding NPCs to my game soon, but I'm a complete novice. Okay, so I don't know what kind of game you're kind of working on, but um, obviously, you're gonna be dealing with you said that your A star is or you're gonna be having NPCs, and obviously NPCs are gonna have to have some kind of way to move around. Um, you're saying you're having a 2D survival crafting game. Okay, um, so you're gonna have your NPCs just kind of walking around. Now, you can, when it comes to artificial intelligence, um, the you can specify, hey, um, well, seeing that it's a 2D, I don't know whether or not you're using like a square or hexagon or whatever, but um, you can, your code for your NPCs, you can basically say, okay, um, you're gonna keep on walking straight until you run into a wall, and then if you hit a wall, turn left or something along those lines. But the problem is that then you're gonna have your AI kind of going around in a circle. Um, especially if it's like a straight, if you have like a square, it's gonna just kind of going, around, you know, in a square pattern every single time. If you just have, you're gonna go straight until you hit a wall, turn left. So, um, so that's why these pathings come into play. Now, with A star, um, yeah, let me go back to um, this particular diagram here, their particular example that they have. So, um, in this particular case here, obviously they're using D star here, but with your A star, you have your start position here and you have your end position there. And then you have objects that you consider as obstacles, you know, places that your NPCs shouldn't be able to walk to or walk through or walk on, what have you. Your walls or your impact, your pits or what have you, places that your NPCs should not be able to kind of walk on whatsoever. Okay, and then you have areas that are completely open for them to walk. These little clear areas. Now they have this gate here that eventually turns into an obstacle. Hence the reason why D star is a little bit more useful in this particular case. But what happens is that um, for A star, you're taking your node, whether it's you taking it from your goal or you're taking it from your starting location. Either case works. It doesn't really matter one way or the other. What um, Where you kind of start off. You could do bidirectional, meaning you you do the A star using both the goal and the start node. So they're gonna kind of expand on their search in both locations. Um, but eventually it will get to a point, it will just kind of keep on expanding out the searches to the point where it just expands until they both find, until you find a path, from one location to another. Okay, that's kind of what A star is all about. Now, if you're doing bi-directional, um, then this map will be pretty much filled in by a lot of searches, but you might actually find the path a little bit faster, maybe. Um, but that's why you know this is what it's saying. Here's the best path from start to finish. You know, on for the D star. Problem is they put this gate there to be an obstacle that stops the AI, your NPC, from moving in that general direction. So it has to reevaluate. Now, A star would start the process all over again. D star uses the information that's already kind of there for you and tries to rebuild the path based off the fact that this obstacle is now there. So, um, so D star is more of a dynamic kind of pathing. Um, but it, the downside that I'm seeing with D star is that you need to kind of store all of the information that um, you're storing more information. So, and based off of the number of AIs you have, that might expand on the overall like RAM kept. So gotta kind of be careful about that. Um, and um, the um, the amount of code that you might need to put in place for D-Star might be larger overall as well. The pseudocode that I'm seeing for the D-Star is pretty extensive compared to an A-Star search. So just bear that in mind because there's a lot more going on in a D-Star than there is for an A star. So if you're a complete novice, then maybe start off with an A star to start off with. See, check what you're kind of dealing with on that, and then maybe expand into a D star if you want to, or try to play around with it. You know, depending on what you uh, depending on what you're kind of facing for the most part. So let's see. Jump point search though. Since this tutorial is about implementing jump point search, pathfinding graph will be represented with the grid. 8-way grid since the algorithm directly uses it. Jump point search really does is eliminate a lot of intermediate nodes and certain kind of grid combinations. It skips a bunch of these you would add to an open list and closed list as well as other calculations in favor of doing some more processing when picking the next node. So with A star, we pick from open scene the node from the lowest F score. This is where things begin to get interesting. Instead of picking adjacent nodes, we'll call this function to do it for us. Okay. Identify successors. Okay. What this does is eliminate nodes that are not interesting to our path. For this, we use direction from the parent to the main guideline. Here are examples of pruning the nodes which we'll ignore for horizontal and vertical directions. Prune neighbors in dark gray. Okay. Okay. See, um, I've removed the forced neighbor checks if the if statements is they're quite large or basically consist of checks that are similar to those. We finished picking neighbors, new node. They serve the purpose of detecting when we are allowed to have our assumptions on symmetry. Um, okay. Now here's where I'm thinking about about this jump point search right at the moment. You would need to have a um, you would need to kind of be able to see where a good portion of the nodes to be able to kind of move to your um, to kind of get to the jump point in this particular case. Dash lines are failed attempts to prevent diagonal jumps. Two jumps occurred from S node to dark node, diagonal from dark node to node G horizontal. So basically, you're having the start node to the dark node as one jump, and then you have another jump from dark node to G mode. Now, obviously, um, from from these particular jumps, you're obviously going to need to kind of do the animation and be able to kind of handle um, the overall movement. But if you don't really have any kind of obstacles from this kind of evaluation, then the jump function might kind of work in your particular in whoever might want it. But my problem is that because I'm using a hex grid, um, it makes jumping a little bit harder. So let me try to explain a little bit. Um, so if it's a straight line, say like say you have like point A to point B and it's a straight line, then that'd be that'd be fine for a jump. But if you're having, point A to point B, that's not so much a good jump. You know, I want, you know, I want them to be able to kind of walk along each one of these hex tiles. So, I don't want them going from point A to point B in a straight line. That doesn't necessarily work in my particular case. So, as much the um, as the um, jump algorithm might, jump point search might be interesting to do, um, it might not work in my particular case. So I think I might need to kind of say no to, um, I might have to kind of say this isn't going to necessarily work out for me. Because um, not only am I going to be dealing with um, changing of directions based off the hex tiles, but we're also have the potential of having, barriers or new paths open or whatnot that, you know, be a little bit more dynamic. So this might not be the best algorithm for in my particular case anyway. So let me see if there's anything else here that might be worthwhile here. Let's see. Cars no extra memory overheads. Um, Consistently speed up an A-star search by over 10 times. But at what cost, though? Gotta be careful with that. You know, are you gonna have your AI units walking through walls? I don't know. So, um, gotta kind of be careful with some of this. Now, technically, it's supposed to be able to like find the walls and say, "Oh, sorry, we can't actually go there." Um, so if you do it right, then it might work out for you. But just be aware that you have the potential of causing yourself some heartache if you do it incorrectly. Um, so um, oh, for if you're curious as to what um, A star kind of looks like a little bit, you can always go to the wiki page, and it has an example for you to kind of look at what an A star is all about. So that's what I kind of appreciated about this particular wiki. It has this example right here, which kind of shows you what an A star is kind of all about. So so in order to find the where it starts off at and where its goal is, it will constantly be searching through nodes as it goes along to see whether or not there's a shorter path, um, or to get to its destination. So it's a good visual of what you're kind of dealing with when you're looking at an A star. So, but once you get the algorithm and the like figured out, then it can be a really good tool um, for pathing, especially if you're not quite sure. Um, if you're kind of new to the game, A star is one of those. Um, it's you can do like um, you can do like a simple like you know walk forward until you hit a wall, turn left kind of design. And I mean that works. Or you can do it, or like games such as like um, like the old Mega Man games or Super Mario games or something along those lines. You had those guys that were kind of walking until they hit a wall, and then they walk the other direction until they hit a wall, and then they just kind of go back and forth, back and forth. Um, you have that kind of AI as well. So if you want something that they seem like they're a little bit more intelligent, then A star is like the next best level That shows that they have a path that they're going to be walking. So, um, okay. Hmm. Same search as before with the A star item. As you can see, you get horizontal and vertical search areas. Next obstacle, light blue points are a bit misleading though, as GPS often stacks several of them in the same location. Interesting. Hmm. Here's a here's apparently um, their performance of what you can kind of see on that. So open queue all length, open queue all length, and then open queue all length. So um, based off of their example, JPS is really kind of helping them out on the overall um, performance. But again, I don't know if it's going to be something that I can use. So I think we're going to have to kind of cancel out jump point search, at least for me. So we're going to go ahead and just remove it completely. I don't want it to kind of jumble up my document here. Okay, now we're gonna move on. Ooh, actually, let's see. It's 5:37. I only got about 20 more minutes left before I have to kind of close down my stream. Um, do I want to get into the next couple search and the next couple of algorithms now, or if I should just kind of stop early? 20 minutes isn't going to give me a full overview of French search, or at least I don't think I'm. I might come to a rush decision if I try doing that. Um, yeah, there's quite a few PDFs and like on that, so this might take me a little bit of time to um, kind of research it a little bit. Now, right now, based off of what I've seen so far, in terms of my game, I'm kind of either leaning on a D star or the LPA. Um, for those of you that are kind of curious, you know, LPA A star, lifelong planning A star. So um, basically, it takes um, it takes your basically takes your entire map, it feels like, and just kind of says, hey, in order to get from point A to point B, you're going to want to go to this particular node, and then you're going to want to go to that particular node, and that particular node, and that particular node, and that particular node. So it kind of saves it all from what I can gather from it. So, um, hence the reason why I want to kind of study it a little bit more and figure out, is that correct? Am I seeing it as something that is going to just do an A star like once for the entire map and show which path is best based off of what node you're at? Now, that becomes a problem when there is like a barrier, or if, say one of my resources suddenly opens up a path, or a new path, then it has to kind of reevaluate itself each and every single time. If I'm saying that the lifelong planning A star is something that kind of does an A star once and that's it. Well, not necessarily once, but you get what I'm saying. Um, the um, Actually, it probably have to kind of do an A star multiple times just to kind of get the right kind of pathing to kind of work the way you want it to. Um, because from what I can tell from this, it basically says, okay, um, here's your start location, here's your goal location, and it will have it already like predefined map going from point A to point B. So when you move from one node to the next node, and you're still trying to reach that one destination, it's going to go, oh, you're trying to reach there? Oh, okay, well, you need to go this direction for that one particular node. If it's a different if it's a different node, or if it's a different location that it has to kind of go to, a different goal, then it's going to go, oh, you have to go up there? Okay, well, you have to go this way. It's so that's what I think happens. So it's supposed to, you're not doing an A star search every single time that you have to kind of do pathing, because you kind of already you know, what node you want to kind of need to go to based off of the A star that was kind of done before. Um, so it might save you some processing power that way, but again, it doesn't feel all that dynamic either. So that's the reason why I'm, on one hand, it sounds really good because I don't have to do an A star each and every single time an AI agent wants to um, find a path. But on the other hand, um, you might have agents taking an old way around when there's a new path that's quicker, based off of the fact that, hey, I just opened up a new path, instead of taking a long way around, now you have a straight path, you know, but the AI agents are just going to keep on doing the old path. That's what I'm kind of scared of for the LPA right at the moment. That's all. That's what I'm kind of worried about. But I think that's where we're gonna go ahead and call it for the night there, folks. Um, we'll go ahead and pick up where we left off next week on Friends Search and LPA next week. Um, we'll look into those a little bit more. Um, we'll see what we can which one of those two might be, if they might, you know, right now, based off of what I know, based off of what I'm I'm needing in my particular game, D star is going to be a little bit better than A star in terms of overall performance. It's going to be a little bit harder in terms of getting the code to be correct and making sure that it kind of works the way I want it to. And I'm probably also going to be needing to store some of the values so that it can, um, so that I can kind of handle the um, fog of war when I eventually do implement it. But um, but so far, the D star is going to be better than the A star. It's going to be a little bit harder for me because I haven't programmed out a D star before, but it's going to be an interesting process to kind of get that to work. So, but next week we're going to look at fringe search and we're going to look at LPA, and we'll see which of those two, um, if they are better overall than the D star. They might be. Don't know. We'll see. We'll see what happens. I mean, Fringe is saying that it's 10 to 40% performance boost. Okay. Don't know. So, and from what I understand, this does the A stars enough to cover the entire map once, and it's done. You don't have to do it over again. So, um, that would require quite a bit of um, quite a bit of storage, because for every node that is going to be on my map, I'm going to need to have, like another node, or I'm going to need to, like for example, for this node right here, I'm going to need to know if a particular person is right here on this particular node, you know, um, what would their path be if they need to kind of go over to, say, this node right over here, for example? You know, um, which direction is it going to need to go to? So it's probably going to need to kind of store all these different nodes, especially for this small map. Once we start getting, once I start going into the other levels, the larger levels, that's a lot of storage. You're talking, arrays upon arrays upon arrays just to store the overall destinations on the maps. So, is that going to be good? I don't know. I don't know about that. Um, but we'll have to kind of see. We'll have to kind of see which works overall. So, but that's where we're gonna go ahead and call it for the night, there, folks. So, um, so hopefully I kind of helped out a little bit for those of you that are kind of curious on pathing. Um, obviously I didn't go in depth on how to actually program out an A star. Um, but I mean, um, there's pseudocode that you can kind of get, that you can kind of look at to understand how these work. So, like for example, the D star has pseudocode for you to kind of work your way through D star, but obviously it's gonna take a bit of it's gonna take a bit of work to figure out, the pseudocode to make sure that it kind of works properly with your game. So, um, and for D-Star, there's a lot of pseudocode. So, um, so yeah, that's where we're gonna go and call it for the night. Um, so all these videos, all these streams that I do are eventually uploaded to my YouTube channel. So feel free to check that out if you like. Got a link down below for that. I also have links to my Discord, my Patreon, and my Twitter account down below on my Twitch About page, as well as in the description of my YouTube videos. So feel free to check those out if you'd like. I have a schedule of everything that I do on this channel down below on my Twitch About page. All the days that I all the days that I stream, as well as the times. Um, these Sundays are my only coding streams, so if you're only interested in um, me developing GGG, then just come on back next Sunday, um, and you can see me continuing the development of GGG. Um, otherwise, you can come on back during one of my other days where I'm, like I have a series on Monday for um, what I call finish what I started, which are basically meant to kind of handle projects that I haven't really finished. Obviously, my game is a project, but it's its own separate stream. I'm talking about like projects um, that I kind of want to do on the side. Little, um, you know, uh, like helpful projects, not necessarily for me alone, but for others. I have projects that are also available. So I have that on Monday. Gonna be continuing my current project of building up a Twitch team, or building up a streaming team, I guess you might say. Um, we're gonna probably be working on um, building up the Discord a little bit more, so um, I could potentially handle incoming viewership on that, as well as get the figure out a way to set up an application process for the team, and then maybe we'll see about trying to see if any partner wants to take it up to make it an official Twitch team. But we'll see on that. But that's tomorrow, and then of course I got my gaming streams on Wednesday, Friday, and Saturday. So if you're interested in those games, which are listed down below on the Twitch About page, um, you can stop on by on any one of those particular days if you're curious. So, but that's where we're gonna go ahead and call it for tonight. So, Finn, thank you for the raid. Thank you for stopping on by. I appreciate it. Um, hopefully, I was helpful in some fashion or another. Again, if you're having some difficulties with A star, um, if you're struggling with like the code or something like that, feel free to kind of reach out to me. As I've mentioned before, I've done A star before on other projects, class projects and the like, so it's not um, it's not something that I haven't done before. So I mean, I can easily do it again. Um, So if you need some help along those lines, feel free to reach out if you're interested. Go to my Discord and talk to me there if you want. Um, um, so uh, I want to say thank you to Seth and Jedi for also stopping on by. I appreciate when you guys do. Hopefully I'll see you all next time. So thank you very much for stopping on by. I appreciate it. Um, I don't know whether or not um, the raid limits are still um, like limited to three or something like that to be an official raid. I don't know. Um, Anyone want to move on to another streamer? I can always send you towards another person if you're interested. Um, don't know if I have anyone right at this moment in time that might be coding. Let's see some gaming channels that I follow, but that's about it. Yeah. So if anything, I'd probably be like picking like a random streamer if you guys are like interested in more like a coding stream or something like that. Up to you. Um, I haven't gotten the. I feel as though I need to have like a, apparently you have like three or more to be a actual raid. I don't know. Uh, I like giving raids, but I like when it's an actual raid and not necessarily a host. Do you understand what I'm thinking? I don't know. That's me though. Um, but um, let me know if you guys are interested. But that's where we're gonna go ahead and close on down for the night. So um, so thank you for watching. I appreciate it. Hopefully I'll catch you next time. But we're gonna say good night. Take care. Stay healthy. Stay safe. I'll catch you strangers next time.